Traditional perimeter defenses like firewalls and antivirus software rely on a simple premise: build a strong wall and keep the threats outside. But against modern, decentralized, multi-vector threats, these reactive perimeters consistently crack and fail. In high-traffic environments, particularly cloud architectures utilizing multi-tenancy, securing the system requires shifting from reactive blocking to proactive anticipation. This requires what researchers call adversarial thinking. Instead of waiting for an intrusion, architects mathematically model an attacker's expected decisions before they ever execute a command. The primary framework for this modeling is game theory. By treating cyber attacks as mathematical games, we can map the interactions between a rational decision maker and the system they are trying to compromise. Securing modern infrastructure means abandoning the assumption that a static wall is enough. It demands the calculus of continuous, dynamic modeling to stay ahead of the adversary. This table outlines the academic taxonomy of game-theoretic methods for cybersecurity. The top half categorizes cooperative and static models, where players work together or make fixed decisions. The bottom right details dynamic, incomplete information models, where the game unfolds in stages and opponents' behavior is unknown. To understand modern cyber vulnerabilities, we have to systematically eliminate the top and left quadrants of this matrix. Mapping an adversary's logic begins by proving why traditional models of cooperation and complete information fail entirely on the internet. Consider mobile ad hoc networks, or MANETs. These are self-organized environments without a centralized administrator. Every individual node must compute its own strategic decisions independently. Cooperative game models assume that in a network like this, nodes will naturally pool their resources to maximize the overall utility of the system. We can test this assumption using a classic mathematical dilemma known as the Stag hunt. This diagram shows the Stag hunt payoff matrix. If two independent network nodes choose to hunt Stag, meaning they cooperate and share threat intelligence, they achieve the maximum security payoff. Let's call it 10 units of security each. But cooperation carries immense risk. If Node A commits its processing power to a shared defense, and Node B unexpectedly drops offline or defects, Node A is left entirely compromised, receiving a payoff of 0. Alternatively, a node can choose to hunt hair. This represents isolating itself and focusing solely on its own perimeter. It yields a lower payoff of 5 units, but that payoff is guaranteed, regardless of what the other node does. This creates a conflict between payoff dominance, hunting the stag for the highest reward, and risk dominance, hunting the hare to eliminate uncertainty. Applying this to an ad hoc network, isolation becomes the mathematically safest choice. When a node faces an unknown threat and cannot guarantee the actions of its neighbors, it defaults to self-preservation. Because coordination cannot be guaranteed, defense models must be strictly non-cooperative. Static, cooperative frameworks are mathematically fragile. Security architects must design systems operating under the assumption that every node will act in its own self-interest. Once we establish that the system is non-cooperative, we must address time. Cyber attacks are rarely single actions. They are sequences of deferred counteractivities. This branching diagram represents an extensive form game tree. It maps the sequential choices between an attacker and a defender as an intrusion unfolds. A public cloud provider uses a tree like this to calculate counter strategies for a finite, predictable set of attack vectors. By mapping every possible move, they seek a stable Nash equilibrium, a state where neither side benefits by changing their strategy. However, this perfect mathematical model falls apart under the condition of incomplete information. In reality, defenders have limited knowledge of the system's live status. More critically, they do not know the attacker's true capabilities or their ultimate goal. Without the attacker's payoff data, the defender is forced to make preemptive responses based on probability distributions rather than absolute certainty. This highlights the flaw in standard dynamic game models. They rely on the assumption that the attacker possesses perfect rationality. A mathematically perfect defense tree is useless if the adversary miscalculates their own payoff or deliberately makes an irrational choice. To account for human deviation from strict utility maximization, researchers integrate behavioral game theory. One of the primary behavioral variables introduced is belief learning. Under belief learning, Attackers change their attack vectors based solely on the defender's past behavior. They may choose an objectively suboptimal path simply because it worked against a previous similar target. Returning to the extensive form game tree, we see how this warps the predictive model. The lines now represent shifting probability weights based on historical data, actively overriding the purely rational paths. Human hackers operate with bounded rationality, heavily influenced by cognitive biases. Consider the break-even effect, also known as sunk cost escalation. This bias causes an attacker to irrationally continue a highly unprofitable, heavily defended attack vector, simply to recoup the resources they have already expended. Similarly, attackers frequently exhibit negative reciprocity. They will actively prioritize punishing an opponent or destroying a target over maximizing their own monetary reward. Human attackers do not play by the rules of pure mathematics. Security architects must incorporate this empirical behavioral data to accurately predict attack paths. In real-world environments, defining perfect, fixed mathematical payoff functions for an attacker and a defender is practically impossible. Returning to this taxonomy table, we can identify the only viable framework for modern security architecture. Cyber attack defense analysis sits squarely in the domain of incomplete information dynamic games. While finding a Nash equilibrium within this quadrant is logically sound, it remains constructively brittle if implemented purely theoretically. The final requirement is fusing this dynamic mathematical framework with empirical data gathered from behavioral game theory experiments. This fused model enables scalable security risk assessment, even within highly complex public cloud infrastructures. These assessments directly dictate business logic. They provide the quantitative basis for deciding exactly how risk liability is allocated between cloud providers and their tenants. Securing decentralized networks is not achieved by assuming adversaries are perfect calculators. It requires mathematically modeling their actual flawed human behavior.